Okay, this is the 15th session. The session is domain is power and energy. So in this session, we have 8 papers, and every author will get around 15 minutes. Okay, so maybe we'll finish in within 14 minutes and 1 minute for question and answer. So after 12 minutes, we'll give a badge for the authors. So, and our first in speech is a invited speech, and this will be provided by Dr. Alexander Anderson. And Dr. Alexander Anderson is a power system research engineer in the distributed systems group at PNNL. His research focus on power systems operation, advanced power application, next generation energy management system, defense against cyber physical threats, microgrid optimization, and human factors in control room environments. Alexander has provided coordinated software integration, testing, and training for multiple power system simulations and applications. He is currently 2022 IEEE Region 6 Humanitarian Activities Chair and IEEE PES HAC Partnerships Chair. Alexander holds a PhD in Systems Engineering from Colorado State University, Professional Science Master's degree in Power System Engineering from Washington State University, and a BS degree in Mechanical Engineering from St. Martin's University. Now, Alexander, floor is for you. Thank you.
Okay, thank you for inviting me today. It is my honor to be an invited speaker at the 4IR conference today. I'm going to be talking about some trends in electric power systems, data integration, and smart grids. We're going to start with an overview of the basics of power systems and then talk about emerging trends. Traditionally, power systems are divided into generation, transmission, and distribution. Generation is defined as the area within the power plant and up to the power plant boundary. Transmission systems are characterized as a large, centralized network with balanced power flow and high observability. And distribution is characterized by unbalanced networks, which have a large number of unknown equipment devices and much lower sensor observability. In the past, there has been very strict boundaries between generation, transmission, and sub-transmission and distribution, with large power plants that are centrally located on the generation side, and then radial networks from the distribution substation to the individual homes. With decarbonization and ongoing increases in renewables, the topology of the power system is changing, and we're now seeing large amounts of renewables connected at different places within the transmission grid, and a large amount of renewables being connected on homes, businesses, electric vehicles, battery storage. All of these new distributed energy resources are changing the way the grid behaves. We also see a significant increase in the amount of data available. Traditionally, communications and power systems have been on point-to-point, air-gapped SCADA networks where there is a dedicated telephone line or a dedicated radio tower that communicates point-to-point between the substation and the utility control center. Now we are seeing a large amount of distributed data streams coming in from homes, from distributed renewables, from battery storage, from synchrophasers and PMUs, and we need to be able to aggregate and correlate this data in a meaningful way. However, there are some major challenges to creating a smarter grid. The first is that in most utilities across the world, electric grid data lives in silos with very little communication and exchange between different software systems. The energy management system is focused on SCADA and real-time data. The network planning software focuses on bus branch power flow, protection settings, new capacity studies, which is again different from a geographic information system, which talks about physical components, where they are located, customer connections, and represents everything in a geospatial format. Again, this is going to be different from the data in the customer billing software, which focuses on metering, rooftop solar, distributed generation. And that is again different from what is in an asset management database, which focuses on the physical assets of a power system, the health of equipment, the lifespan of transformers, substation configurations. All of this information is different and in different formats across each of the silos. The second challenge is silos of technical expertise. When we bring different experts from the power systems domain, they have different technical areas of focus and often use different words to mean the same thing. The control room operator or the control room dispatcher is focused on the SCADA interfaces, interacting with field crews, safety-related procedures, which is very different from a power systems engineer who is focused on power flow models, system protection, and load forecasting. And it again is different from an application developer who is focused on creating new innovative algorithms and ways to make use of new devices. And that is also different from the cybersecurity defender who is responsible for making sure the software systems and the computer systems are secure and running in real time without interruptions. When we look at the difference in perspectives between engineers and dispatchers, we see a major difference in the way they view the world. Engineers are abstract, analytical, formal. We care about efficiency. We care about optimization. We want cutting-edge technologies. We want to be at the forefront of that fourth industrial revolution. The dispatchers working in a control room, especially within the United States, are very skeptical of new technologies, and they have a strong emphasis on safety, situational awareness, and responding to events in real time. If we start to transition to a deregulated market structure where we introduce energy markets, auctions, bidding, and aggregation and retailing of electricity at the distribution level and transmission level, the picture becomes even more complicated. And now we have layers of regulation, reliability coordination, markets, and then basic control and operation. So how do we navigate this really complicated domain space? We need data integration and we need smart grids. Data integration is the concept of creating a data-rich environment that allows power system applications to leverage new and existing streams of data. Existing data streams include SCADA, field telemetry, measurements from large distributed energy resources. We also have existing data that is aggregated not in real time. Advanced metering infrastructure, smart meters, you go to almost any utility across the world, they get real-time measurements from their smart meters, but they don't get aggregated until the next business day. So we have perfect knowledge of what happened on Friday, but we don't know what's happening right now. And we also have new emerging data streams that are being created by the fourth industrial revolution, from Internet of Things devices, smart inverters, micro PMUs, and we need to be able to make sense of this. Well, what does a smart grid actually look like? We can look at it at both the transmission and distribution level. At the transmission level, we see a greater integration of standards. We see faster communications. We see the creation of wide area measurement and protection networks based on synchrophasers, based on fiber communications, and based on more efficient communications protocols, such as routable Goose and IEC 61850. At the distribution level, we see a higher penetration of controllable resources. We see battery storage. We see electric vehicles. We see a local generation. We see a higher amount of controllable switching devices, such as intelligent reclosers. And we have all of this data that needs to be brought together and synthesized. Well, how do we do that? Part of the answer is we may need to reimagine the way power system software is built. Most of the utilities across the world are using power system software that was originally written in the 1980s and 1990s. Your GE EMSs, your Alstom, your Siemens, these energy management software are all structured the same way, where you have a generation component to the software, you have an energy management display with the core power applications, such as contingency analysis and state estimation. And that is completely separated from the distribution grid software. You go into the dispatch centers of many distribution utilities, even in the United States. You go in, they have one computer display, and for everything else, they keep track of outages, equipment statuses. There's a giant paper map of the city, and they keep track of the equipment using Post-it notes and thumbtacks. And this is how they run the distribution grid. As we transition to the fourth industrial revolution, we need to have a different philosophy of how we build software that spans the generation, transmission, distribution space. And this will be extremely important as we start seeing greater and greater penetrations of solar, wind, battery storage, electric vehicles. We need to be able to integrate them into a flat, layered software architecture where we're able to bring in transmission data, distribution data, meter data, and we need to have a standards-based approach so that when we refer to a particular type of device, it's the same class of device across different software systems. Well, how do we do that? That is a very difficult task, but there are some resources that we can use. And one of them is the Common Information Model. It's an open source information model that corresponds to a set of IEC standards and provides us a way of
2 minutes more.
Got it. Thank you. It gives us a way of exchanging data across different applications and services with a common data format. Finally, we're going to talk about some of the potential for machine learning. We've been talking about artificial intelligence in power systems ever since Wollenberg wrote an original paper back in 1987. And we've talked about expert systems, fuzzy systems, neural networks, and there are certain opportunities that could benefit from machine learning, such as better state estimation, better forecasting, better prediction of climate impacts. We're going to talk, though, about some of the challenges because you go across utilities worldwide. Artificial intelligence has not been adopted except for a handful of forecasting applications. Part of the reason is that it is very hard to apply machine learning to power systems. Data patterns are only valid for one network topology. And if you change the topology, such as you open a breaker or a set of breakers and a breaker and a half or a ring bus substation, that changes the power system and now you need new training data. It's also very difficult to model abnormal grid configurations and create training data sets for emergency operations. And that is the situation when dispatchers really need machine learning the most. We can talk about a couple of general recommendations for providing a sanity check to machine learning applications. And we can derive that from the aerospace industry. We teach aircraft pilots to fly by the looks right approach. And machine learning for power systems needs to take the same approach, where it uses easily recognizable patterns of equipment statuses, anticipated values for current conditions, conflicting data. If one sensor says open, the other sensor says closed, we know we have conflicting data, and that is a problem. We can train machine learning to look at that and provide a useful piece of information, especially during emergency conditions. There's one final piece of information that we can also take from the aerospace industry, and that is a couple of lessons learned from the 737 failure. Automated systems in machine learning should not be allowed to override the dispatcher. They need to have a master cutout. It's important to have the correct architecture and ensure that the machine learning has been tested in emergency conditions and failure scenarios. And you must develop it with the dispatcher in mind and train them in a simulator across normal alert and emergency operations. And that wraps up my presentation. Thank you very much.
Thank you, Alexander, for a nice presentation. So we can take a couple of questions if you have any questions. Okay, the question was, is there any scope to contribute in Bangladesh, I mean, from your research outcome? And what are the scope you can foresee that you can apply in Bangladesh? I mean, considering that we are thinking that Bangladesh grid is weak grid and we have very poor, communication or internet infrastructure. Considering all these things, what do you foresee or what are the scopes in Bangladesh to, adapt the smart grid and smart systems in our power sector?
It's the most important to take a reliability focused approach. So from conversations I've had within the past few weeks with people from PGCB, I understand that Bangladesh has some generation capacity shortages. And so it could be that intelligent load shedding may be very useful for the Bangladesh dispatchers, so that if there is situations where there is extreme demand, we teach dispatchers in the US to shed a load before any emergency occurs. People will be upset with you for doing that and say, oh, you caused us a local blackout during the holiday. But in the US, we teach dispatchers this is more important to keep the bulk grid stable. And as Bangladesh adds more generation capacity, it will become more stable and easier to operate. Dispatcher training is also an extremely valuable tool so that you can take the control room operators through various emergency situations and make sure they have the skills to deal with any issues that come up. These are the cheapest solutions. And then, of course, as you build out internet infrastructure, as you build out communications, you can start introducing smart grid concepts. But it's important to start with basic reliability related tasks.
Okay, thank you very much, Dr. Alexander Anderson, for your nice presentation. So now we can give a big clap for him. Yeah. Okay. Thanks again, Dr. Alexander Anderson.